Greetings and salutations, magical chemists. Today we're going to talk about aqueous calorimetry. Now, many calorimetry labs involve adding a solid, like, an unknown metal, to a water bath to determine the temperature change of the water bath. However, there are multiple times when you need to determine the energy change of an aqueous reaction. That could be determining delta H neutralization for acid bases, or delta H solution if you're dissolving a salt. So there are 4 important assumptions that are made during an aqueous calorimetry lab. These should be stated for you in the problem, and if they are changing them, they should tell you. However, it's really good to know. First, we assume the density of the aqueous solution is the same as water, 1 gram per milliliter. We also assume the volume of the reactants are additive. If you add 100 mils of one reactant to 200 mils of another reactant, you will get 300 total milliliters. We also assume that the specific heat capacity of an aqueous reaction mixture is the same as water, 4.18 joules per gram degree Celsius. And we also assume, even though we know this isn't true, that heat is not lost to or absorbed by the surroundings. At least we assume that until we're talking about lab error. Now, the normal calorimetry math still applies, but when you have aqueous calorimetry, you are not going to have those double MCAT, where MCAT equals negative MCAT and all those variables. You're not going to have those. Instead, you have to add the masses of all the chemicals reacting. That even includes just the water, if you're dissolving something in water. Because the heat that's absorbed or released during this change is being shared by all of the chemicals present, and that includes the water. So, just like normal, we could say that the Q of the reaction is equal to negative the Q of the calorimeter. They are, of course, equal but opposite in sign, because if one gains, the other loses, and vice versa. Now, of course, if you're not just trying to calculate the energy change, but you instead want to find delta H, good old enthalpy is always divided by the moles of reaction. So you calculate Q, calculate moles of reaction, divide. Now, remember how I was talking about lab error? Well, turns out almost all the lab error with calorimetry comes to the flaws in assumption number 4. That whole thing about saying heat is not lost to the surroundings. yeah, it is. So, the calorimeter itself can actually absorb some of your heat, or the heat can be lost to the surrounding air. Both of these errors would make your calculated delta T, your change in temperature, less, which would lead to a smaller calculated energy change, smaller Q, and thus delta H would be smaller when you calculate it than it should be. So let's go ahead and try a couple of practice problems. So in our first practice problem, we are dissolving sodium carbonate in water, and it was exothermic, a temperature increase was observed. So they want you to calculate the enthalpy of dissolution. It always sounds so fancy. The way we write that is delta H of solution. Remember that delta H is implied to be in units of kilojoules per mole reaction. So we have 2 calculations to do. First, we're going to go ahead and calculate the amount of energy released when that specific quantity of sodium carbonate was dissolved. Well, that's an MCAT problem. You're remembering, of course, that Q of the solution, which is what we're trying to find, is opposite in sign for Q of the calorimeter, which is what we're going to calculate. So we need to plug into MCAT for the calorimeter. When you're doing this, remember to add the mass of both the sodium carbonate and the water. For the specific heat capacity, they told you that it was the same as water, so it's the 4.18. And for the temperature change, we do final minus initial, but actually, we didn't get to subtract anything here. They told us it went up by 3.8 degrees Celsius. That's your delta T. So then you just plug it all into your calculator. Remembering, of course, that the answer you get is in joules because of the units from the specific heat capacity. Also important to note is that you would only get to keep 2 sig figs here because there were 2 sig figs in the temperature change, but I'm not going to round yet because I'm not done with the problem. However, I am going to convert this straight to kilojoules since it needs to be in kilojoules for my calculation of delta H. Okay, got my kilojoules, but now I need to find my moles of reaction. Luckily, when you're dissolving a salt, for salt dissolution, there's always just one formula unit of the salt. So the moles of your salt are the moles of a reaction. So we just need to convert our grams of sodium carbonate to moles of sodium carbonate. So you're basically just dividing by the molar mass. Now, you don't have to justify this, but I wanted to make sure you understood why I could convert directly from sodium carbonate into moles of reaction. When you write the dissolution, it's not really reaction because it's dissolving, but when you write the dissolution expression, you're showing one sodium carbonate breaking apart into its ions, but the stoichiometric coefficient of that is 1. So, stoichiometric coefficient of 1 means 1 of that for every 1 mole of reaction. But luckily, you don't have to explain that. You are allowed to just do it. So last but never least, we need to plug into our delta H expression, which of course just means take your number of kilojoules divided by your number of moles. Remembering we only got to keep 2 sig figs from our calculation of the kilojoules. So ultimately, we get the value of negative 26 kilojoules per mole reaction for the enthalpy of solution or dissolution for sodium carbonate. All right, let's try another one. But this time, you're going to calculate it. This one is mixing an acid and a base. Ooh, fun. But now you want to go ahead and calculate the enthalpy of neutralization in kilojoules per mole reaction for this particular reaction. But this time, you're going to do it because you know what to do. So when you are ready to check your answer, unpause the video. First, you calculate the energy released by plugging into MCAT, remembering to take the opposite sign. And then, in this particular case, to find the moles of reaction, you do need a balanced equation, but at a glance, you might be able to balance it. NaOH only has 1 OH to donate. NaHCl only has 1 H+. So that means it is a 1-to-1 stoic ratio. And because it's 1-to-1, the moles of either chemical, since they're equimolar, are going to be equal to moles of reaction. This means you could pick either the acid or the base and use them to calculate the moles of reaction, and you will totally get the right value. So first, I pick one of them, and I multiply to get the moles, and then I convert from the moles of whichever chemical I picked into moles of reaction, which is 1-to-1. And finally, I plug into delta H, giving us a calculated value of negative 55.7 kilojoules per mole reaction. Let's try one more that's just a little more interesting, shall we? Now we want to determine the enthalpy of neutralization for sodium hydroxide reacting with phosphoric acid. Notice this is not a 1-to-1 reaction. This is a 3-to-1. So this is going to make our lives just a little more fun, but we can totally do it. The first thing we need to do is calculate Q of the reaction, how much energy was released when this reaction happened. So go ahead and do that, and when you're ready to check your answer, unpause the video. So this particular reaction released 815 joules of energy. And now we want to calculate delta H, neutralization. And they said, okay, calculate it if the initial molarity of both solutions is equal to 0.80 molar. So they're equimolar. But here's the thing. Equimolar actually means, because it's not a 1-to-1 ratio, one of them is going to be limiting. Which one? Well, think about it. Every time this reaction runs, it uses up 3 sodium hydroxides, but only 1 phosphoric acid. That's a 3-to-1 mole ratio. So guess what? Your sodium hydroxide is being used up 3 times as fast, which means you're going to run out of it sooner if you have equal amounts of both. So your base is limiting, so you have to use the amount from your base. Once you've calculated the moles of base, it is particularly important that you calculate to moles of reaction, because of course the stoichiometric coefficient of sodium hydroxide is not 1. It's 3. So you're dividing by 3 when you're converting to moles of reaction. And now we have the values we need to plug into delta H. And when we plug in our values, we get a final answer with only 2 sig figs of negative 120 kilojoules per mole reaction. And that's it. That's aqueous calorimetry. So thank you for playing with the glories of chemistry.